I met Matt through Steve Dance, which is of course why I've organized Steve to be here. And yeah, because Matt has sort of dual lives doing that, but that are combined by I guess ice thermodynamics. So his hobby is I believe planetary habitability, and thinking about ices on ocean walls at high pressure. And his real life is saving organs by freezing them without destroying them.
Something like that, without destroying them. Yeah, that's the
Something
goal.
along those lines. And
Yeah.
since he's just started as assistant professor over at Texas A&M, I thought it'd be just excellent to invite him over and introduce him to the crowd and direct the crowd to him.
Perfect.
We should get more of the Texas people talking. And
Absolutely.
Yeah.
So welcome.
Thank you.
And yeah, without further ado, please.
Awesome. Well, thank you for that sterling introduction, Mark. So yeah, Matt Powell-Palm, Texas A&M. I'm sort of split over there between the departments of mechanical engineering, material science, and biomedical engineering. You'll notice that none of those are departments that say planetary science or earth science or geoscience or any of this. So as I was talking to the grad students at lunch, there was a lot of there were words being said that I'm like, oh no. Like, oh yeah, I work on impact cratering, blah, blah, blah. And what did you introduce me to? Geogenic arsenic.
Yeah.
I was like, this is going to be what an adventure. So my talk today is called Chaos and Confinement, Mastering Thermodynamics, the Thermodynamics of Water at Low Temperature. And without any further ado, let's just get on into it. Let's see if how do I activate these slides? Here we go. All right, so my lab at A&M, our core concern is the thermodynamics of water. I am a materials thermodynamicist by trade, and we study water as a model system because it then allows you to wander into application domains that touch like every aspect of life as we know it, right? So as Mark said, a lot of our chief applications are in the medical space. Medicine as a whole is a water thermodynamics problem, water and organic chemistry, agriculture. You have this sort of awesome macro level water thermo problem, which is managing the water resources of the planet as a whole, and then also very micro level water thermo problems, looking at basic food scientists, food chemistry, food preservation. We work a lot in ocean ecology, trying to protect endangered coral species from ocean acidification and thermal changes. But you can sort of envision the entire ocean ecosystem as one big water thermo problem. And then, of course, one of my more recent interests, looking at the thermodynamics of water abroad amongst the stars, right? And thinking about how the water thermo that we think of for these other applications might affect the prospect of habitability in space. So the overarching sort of thesis statement of my broader research group is that if we can untangle new aspects of the thermodynamics and kinetics of water, then we might be able to find fundamentally new ways to tackle these grand challenges that we face in the 21st century that are broadly disparate at their face, but are unified by a concern with water. So with that said, today we're going to try and touch on two challenges, time permitting. One is the understanding of icy worlds in our solar system, and the other is mastering low temperature biopreservation. One of these might sound more familiar to you all than the other, but we'll see. So here's my formal written disclaimer. So you can't say I didn't tell you so. I am not a planetary scientist whatsoever. I come from the sort of cut and dried water thermo background, and I wandered into all of this through Baptiste Janot at University of Washington, who called me up one day out of the blue and basically told me that this broader effort to understand icy worlds, in particular icy oceans, requires more water thermo. And so that got me interested, and there's actually a lot of overlap that we'll touch on later on between my formal training, which is in the field people call cryobiology, the combined thermodynamics of low temperature water and life, and then astrobiology and icy worlds. A lot of overlap. Okay, so token motivation slide. Steve, let me know how I do on this. Icy ocean worlds in our solar system present some of the most intriguing candidates to host life abroad. And over the last couple of decades and into the next couple of decades, we have put an unbelievable amount of energy, not only intellectually, but also in terms of dollars, into starting to explore these interesting foreign bodies that have these just massive reservoirs of liquid water, or we think, and of exotic ices and interesting inorganic and organic chemistries at play. And so what I think about, the way I think about the thermodynamic premise of understanding icy worlds is that we're going to, over the next few years, be getting a ton of new data. And what I want to contribute to, what my lab wants to contribute to, is sort of developing the fundamental thermodynamic background. We need to be able to parse that data, understand what's going on, and make the most informed sort of calculations and interpretations that we can. So I show here a cross-section of a Europa-like body that sort of lays out some of the ways that equilibrium thermodynamics intersect with the challenge of profiling these distant icy worlds. So we have all of these complicated transport and kinetics phenomena. You know, we have these crazy impact cratering events and cryovolcanism and percolation of the brines and solid and liquid convection processes, exchange of nutrient materials from the inside to the outside, so on and so forth. You have all of these interesting transient processes that, like all transport and kinetic processes, are ultimately constrained by the equilibrium thermodynamics of the systems of interest. Okay, so for instance, if we think about the thickness of the ice 1H layer at the top of a world like Europa, this is fundamentally constrained by the equilibrium between the liquid ocean and ice 1. Okay, so just knowing things as simple as the melting point of the plausible liquid layer here is so important to being able to put limits on our modeling of these transport processes. But ironically, this phase space that we're entering when thinking about these high pressure, low temperature oceans is just fabulously underexplored, right? So when you think about what we know about water and its solutions, we know a ton between 0C and 100C. We know just an unbelievable amount. And then we know that over a moderate range of pressures and over a relatively small subsection of possible chemistries, typically, you know, solutions that have at maximum 2 or 3 components. So in this new phase space of interest at low temperature and at high pressure, and especially in chemically complex environments, we're just missing fundamental aspects of the data that would be required to make quantitatively accurate estimations of any of these more complicated planetary processes. So our goal here is to start establishing limits based in equilibrium thermodynamics on the properties of interest that dictate, in particular, the stability of liquids that might exist in these ocean worlds. Okay, so to start grappling with this premise of stability, important to give a little bit of basic thermo background, right? So the first concept that we need to think about is the eutectic. Right, so I think everyone here has seen a binary phase diagram. They know that the eutectic is the point at which a liquid can transition directly into a solid solution without going through a 2-phase liquid-solid regime. I think more importantly, interpretation-wise, the eutectic is at a given constant pressure the limit of temperature stability of the liquid phase, right? So you could say if I unconstrain my composition, I'd say the composition could be whatever it wants to be on the x-axis here, then the eutectic gives the lowest temperature at which the liquid could still exist stably, right? So binary eutectics like these, very well documented at atmospheric pressure, shockingly poorly documented at high pressures, right? Even for the most simple water salt system. So it's maybe before I start talking about what we've actually started doing here, let's zoom out a little bit and think, why? Why are these things so poorly documented? It's not that we didn't have the motivation necessarily, it's that documenting them is incredibly hard, okay? So I show here now in 3D with pressure as an axis, the same binary phase diagram. The eutectic PTX curve is this red curve going down the middle here. And you can imagine that you have this very large 3-dimensional parameter space where you're trying to identify the coordinates of a 1-dimensional spline, okay? So if you're just searching in concentration and in pressure and in temperature, then you have to do an unbelievable number of tests to constrain this line. And these are tests that are experimentally cumbersome because you're operating at very high pressures, hundreds of megapascals. And then, they're tests that also don't lend themselves to working in very small volumes where high pressure is easy to deal with, because at very small volumes, you start to be plagued by the issue of metastability in a lot of these high pressure phases that might emerge. So conventional approaches that people use for high pressure thermodynamics, like the diamond anvil cell or pressurized DSC, these become very tricky and time inefficient when you're searching this large parameter space for this small amount of data, right? And so the original way that I got into this was that Baptiste approached me about a technique I was working on to reduce the number of tests that you have to do to search this parameter space. So the topic of my PhD, again, as applied to organ and tissue cryopreservation and other topics in medicine, but with interesting crossover here. Topic of my PhD was this premise of isochoric freezing, okay? So in isochoric freezing, what we do is we take a bulk volume sample, so think 5 milliliters, and we constrain it in a constant volume chamber, so some rigid body absent air. It's shown schematically in the bottom left here. These are extremely simple devices. Imagine, 7075 aluminum jar with a pressure transducer on it. And when you constrain the volume of a liquid, all of a sudden everything about its thermodynamics is transformed, right? So we're used to dealing with liquids at a constant pressure, where either it's at a constant pressure because it's exposed to the atmosphere, or because we are controlling the pressure. But you think about Le Chatelier's principle and the sort of correspondence between different thermodynamic conjugate variables. If you confine the volume of a liquid instead of controlling its pressure, now it is free to respond in pressure as you change other parameters of the system. So if we think to Gibbs phase rule here for a second, in a binary system, we have one intensive thermodynamic degree of freedom, right? So this means that I can change either temperature or pressure for a given univariate state. I can't change them both. And practically, what this means for us doing isochoric freezing is that if we confine the volume of the system and allow its pressure to respond instead of controlling its pressure, then we can only change the system's temperature and the equilibrium pressure will emerge, right? So isochoric freezing gives us a way to directly measure this eutectic curve by taking a eutectic composition solution, putting it in an isochoric chamber, and simply cooling it down and melting it, right? So just changing its temperature, the equilibrium pressure that emerges based on the change of interior volume when phase change happens just comes out and we just have to read it, right? So now we can search this large three-dimensional parameter space by varying only one variable, temperature, and we can get this 1D spline, okay? So our initial trials doing this were really exciting. So we took a number of salt systems of interest to icy worlds, and we just went and measured their the pressure dependence of their eutectics over 20 or 30 degrees. And you can see here that for the scant literature data that was available, the results we got agreed really well. And something I want to point out here is that with this technique, again, because we don't have to control pressure, and because we aren't using an optical evaluation technique like a Ruby technique or a fluorescence-based technique, we can get insanely repeatable and low error pressure measurement. So you almost can't even see the error bars on these markers, but the error bar we get with the isochoric freeze melt technique is about plus or minus 1 MPa. When you look at conventional like high pressure diamond anvil cells with optical evaluation techniques, you're usually looking at plus or minus 10 to 20 MPa, right? So like you look at the size of these error bars from some of the really seminal work in this field, and it shows us that this isochoric freezing technique, by sort of leveraging very simple thermodynamic tricks in the system, can yield really high accuracy, temperature, pressure measurements of the eutectic curve. And then also really high time efficiency in these measurements. So each of these curves, as you can imagine, we just take this chamber with the given solution, we put it in some automated bath where we cool it down and then we warm it in controlled steps, letting it stabilize at each temperature. We read the pressure, that's it. So I can run, say, 3 of these at a time. I can put it in at 5 p.m. when I leave, and when I come back at 9 a.m., I have this fully constrained curve. So I'll note that to when we were first doing this, to sort of check that we were indeed reading the eutectic pressure temperature trajectory as opposed to some other pressure temperature trajectory. We did some sort of thermodynamic due diligence where we tested a variety of off concentration eutectic starting compositions, I should say non-eutectic starting compositions. And you can see here that we get the behavior that we should expect from Gibbs phase rule, where, you know, for two-phase equilibrium, so just the liquid and ice, there should be a variety of different starting points in concentration that will yield a variety of different curves. But when you hit the eutectic composition, where you have 3 phases simultaneously present, ice, the liquid, and then the solute-bearing solid phase, you only have one thermodynamic degree of freedom. So at any given temperature, there are no options for your pressure or your concentration. Everything must converge to the same line. And you can see here that it does. Because when we start at these lower concentrations, as it's freezing in the 2-phase region, you get solute rejection that ripens the remaining solution to the eutectic concentration at that pressure, and then everything converges onto the same eutectic line. So we then went to try and contextualize a little bit about these different pressure dependencies of the eutectic that we were seeing in these salt systems. So what I'm plotting here now is the eutectic pressure against the difference, the delta in temperature between the atmospheric pressure eutectic temperature and the temperature that we read, right? So you can think of this as the freezing point depression of the eutectic point. And you know, this of course jumped out to us immediately because we take these very different starting scenarios, you know, that are 25 degrees apart, and then when we plot them in terms of eutectic point depression, as opposed to just eutectic point, we see that they all collapse onto one curve. And then, not coincidentally, that curve sits perfectly atop the freezing point depression of pure water, right? So this sort of led us to an initial rule of thumb that we could maybe, for a wide variety of salt systems in water, approximate the pressure depression of the eutectic temperature using the pressure depression of ice 1H, right? So however much you would shift the ice 1H melting point is how much you'll shift the eutectic temperature. So what this, you know, the reason this makes sense to us, right? Or I should say, when we went back to look at this a little more carefully, we decided that this should be logically consistent because the phase volume difference between water and ice 1H is huge, right? We're talking about a 10%, 9% difference, wherein the solid phase is less dense than the liquid phase. So water's weird, uniquely large volume difference means uniquely responsive to pressure. Whereas when you look at the pressure dependence of the liquidous surface of the solid solute phase, like hydrohalite in NaCl, these are relatively insensitive to pressure, right? So just because water ice has this incredible thermodynamic dependence on pressure, that's dominating the behavior of the eutectic as a whole, and the relative pressure sensitivity of the solute phase is just not contributing a lot. Okay, at this juncture, I want to shout out my rock star master student, Brooke Chang, who pursued a lot of this early work. Okay, so there's a couple of other interesting data points that we can extract from these types of data streams, these PT eutectic coordinates. One thing we can do, if we have a 2-phase liquidous surface, you know, some understanding of the melting surface of the solute solid phase, we can actually project the eutectic PT trajectory onto the liquidous surface of the solute phase, and we can get an estimation of how the concentration then changes along this PT eutectic line. So these are the now estimations of the entire P, T, X pressure temperature composition coordinates of that three-dimensional, or I should say one-dimensional eutectic spline that exists in 3D space. And then we could also do things like, play thermodynamic tricks applicable to any kind of univariant, first order phase transition. We can play these thermodynamic tricks on the eutectic, so we can do things like apply a Clapeyron relation to this eutectic curve instead of a pure material curve, and back things out like the enthalpy of fusion of the eutectic reaction, or if you have the enthalpy of fusion of the eutectic reaction, you can back out the phase volume difference. So not important, but I'll note that we've barely scratched the surface of how we can just through classical thermodynamic analysis extract more data from these PT eutectic data sets. Something to think about if there's anyone in the audience with a really strong classical thermo background. Okay, so we started exploring these eutectics. We had some interesting results. Maybe the most obvious question that should jump to your mind looking at this first data set is, well, how far does all of this go? Right, so we're seeing here that as we increase the pressure, we're depressing the coldest temperature at which a liquid can exist. But how much can we do that? How far can we depress that temperature? So we started thinking in terms of this new lingo of looking for a limit on the limit, right? The eutectic is the constant pressure limit. Now, what if I unconstrain pressure? What is the ultimate limit of stability of the liquid phase? So that led us to introducing this new concept, the cenotectic. So cenotectic comes from the Greek. I could try and pronounce this, but you don't want me to. I think it's koinos. Yeah, yes, I did. I actually asked a Greek classics PhD student friend of mine. I said, hey, eutectic, the etymology was easy melt in Old Greek. Find me a better one, meaning the universal limit. So universal melt is given by cenotectic, right? So we're now proposing this new concept in materials thermodynamics of an invariant point that occurs at the lowest temperature at which the liquid phase is stable for any value of concentration, pressure, or any other thermodynamic force acting on the system. Okay, so this cenotectic terminology that we're proposing, this concept, is trying to get after the idea that for any phase space that is available to a system, there is some temperature at which that represents the absolute lowest temperature at which the liquid can exist. And we actually can know a lot about this temperature just by referring to Gibbs phase rule and tenets of classical geometric thermodynamics. So one thing that we know, obviously, is that it has to be an invariant point, meaning it has to have zero intensive thermodynamic degrees of freedom. So this gives us the ability to, for instance, for a given number of components, the ability to tell how many phases will be present. So in a binary system, the cenotectic point will always have 4 phases present, right? And we know also that it must definitionally always occur at the intersection of at least 2 univariant, so 1 DOF, multi-phase lines that have opposite Clapeyron slopes, dp dt slopes, right? And so this is sort of a fundamental consequence of the fact that in Gibbs's simple system, right, the system, all systems are affected by both thermal work, some temperature times entropy term, and mechanical work, some pressure times volume term. So this point exists necessarily in every system. Now, I will note that for aqueous solutions, because ice 1H is less dense than liquid, the cenotectic will generally occur at higher pressures, right? Where we'll keep pressurizing, right? You can imagine we started this eutectic. This is sort of the curve that we just saw. We depress our eutectic until we hit some point where now the ice 1H in the system is going to convert to a denser phase of ice. And then if we continued applying pressure, the melting point would start going up, right? So there's some necessary minimum. In aqueous systems, because of this ice 1H versus denser ices relationship, this minimum is at high pressure. I'll note though that for systems that are not like water or silicon or gallium or things with less dense solid phases, if you were to look at like iron, then in fact this cenotectic point will be at sub 1 bar temperatures, and it will involve equilibrium with the vapor, liquid vapor solid, and liquid solid solid, right? So the fact that it occurs at high pressure is a unique is unique to systems that have less dense solids than the liquids. Okay, so we did some thinking about this idea of the absolute limit of temperature stability. And we did a little bit of thinking about the sort of geometry of the phase diagram and how we would get there and so on and so forth. And then, the next step is to see, can we go ahead and measure this using the isochoric freezing technique from the previous slides? Turns out we can. So what happens is that as you pressurize essentially the eutectic curve, you'll depress the melting point onward and onward and onward and onward and onward until you'll actually see the ice 2, ice 3 transition, and the entire system will solidify, right? So we went and we took now these same systems and a few others, and we carried them as low in temperature as we could until we saw this transition to the denser phase of ice, and then this intersection marks the cenotectic temperature, or the absolute limit in temperature that is achievable for any value of concentration or any value of pressure within that system. So, in these initial data sets, it sort of jumped out to us that we can, formalize or we can contextualize the cenotectic concept a little more richly by thinking about sort of different relative molar solubilities of different salts. So you can see, like, we show like a low solubility surface up here that corresponds to sort of this group, and a middling solubility surface that's right here. And then you can imagine that, as you go to higher and higher solubilities that have lower and lower atmospheric pressure eutectic temperatures, you'll actually cross this boundary here, where then the denser phase that you run into over here, instead of being ice 3, like it is for these guys, it will end up being ice 2. And this is intriguing because these things might have really, really, really low cenotectic temperatures given the slope of this ice 1, ice 2 liquidus curve as you keep going down in temperature. So something to look at. Increasingly difficult, I'll note, to measure the cenotectic experimentally as it occurs at lower and lower temperatures, just because the kinetics of the solid-solid phase transitions in the system get really sluggish. We're working on different sort of new ultrasonication methods to speed these things up, but it's challenging as you go to lower temperatures to do any of this phase transition analysis. And then, of course, when we collapse these curves onto a pressure depression of the eutectic temperature axis, like we did before, we see the exact same rule of thumb actually holds all the way to the cenotectic point for a variety of different systems. Okay, so we've sort of solidified this rule of thumb that for simple eutectic systems, and I'm defining simple here as things that don't have a bunch of other phases between the eutectic and the solid solute phase. The cenotectic will generally occur at the same place that the triple point occurs for water and ice, right? Where that denser ice transition happens. So this is generally about 22 degrees Kelvin below the atmospheric pressure, eutectic temperature, and 210 MPa. Okay, so this is our sort of the rule of thumb that we're now applying to simple eutectic salt systems. Now, what about when they aren't simple eutectic salt systems? Well, turns out one of the big stories to me in the last 5 years of aqueous thermodynamics at low temperature, high pressure, is that we had just no idea how many fascinating, crazy phases of interesting solute-bearing hydrated solids exist at low temperature, high pressure, right? So these curves now, this is what you see when you start to run into other intermediate phases en route to your cenotectic. So these are non-simple eutectics. So every time here that you see a kink in the PT curve, there's some kind of phase volume difference happening, some step change that represents a phase change, right? So this shows NaCl, NaHCO3 and MgCl2, right? And in all of these, we detected new phase transitions that generally had not previously been reported, which was fascinating. So the first of these, the timing was really good. Baptiste and Steve and co, just last year had this brilliant PNAS article where they found a couple of new phases of high pressure hydrated NaCl. It's like you think about water NaCl, one of the most studied phase diagrams on the planet in history, and yet they go to low temperature, high pressure, they find all this crazy new shit happening. So we were able to actually confirm Baptiste's earlier findings with this transition that we observed here. So we were able to confirm the pressure at which he had estimated that this SC 8.5 phase should emerge. And then in the MgCl2 system and the sodium bicarbonate system, we then went to Grenoble and got some time at ESRF and did some single crystal XRD and haven't published these structures yet, but found interesting new structures corresponding to each of these phase transitions. And this, I think, we're just really scratching the absolute tip of the iceberg here in terms of the diversity of like potentially hyperhydrated, high pressure, low temperature phases that exist out there, right? And so a couple of things that I'll note to you. One, all kinds of interesting treasure hunting to be done at low temperature, high pressure. Two, the isochoric freezing technique turns out to be actually a really interesting high throughput method by which just to hunt for low temperature, high pressure phase transitions. And then three, just note that these additional phases will always, or I should say, will almost always, will generally raise the cenotectic temperature relative to the pure phase, right? Relative to the simple binary case. So here we were absolutely plagued by slowness of solid-solid transition, sluggishness in the kinetics and metastability, right? So we couldn't pick out the final cenotectics. But at equilibrium, they'll actually go sort of like this, where there will always be an increase in pressure necessarily at the phase change. So we can guarantee that at equilibrium, these other phases can only raise the cenotectic temperature, which to us says that the 22 Kelvin, 210 MPa rule of thumb still represents a good limit on the cenotectic for aqueous salt systems writ large. Okay, so with all of that in mind, you might ask, okay, how does any of this relate back to planetary science? So in icy worlds, where we're worrying about this ice 1H layer and the volume and composition and state of this ocean, the cenotectic dictates the maximum pressure at which the liquid can remain stable, right? And now the pressure experienced in this ocean is of course dictated by the ice 1H layer thickness and the planetary gravity. So we can now just define this concept of a cenotectic ocean, some kind of an endgame ocean, where we say, hey, at the absolute coldest the system could be and still have liquid, we can actually go and calculate, based on the cenotectic pressure, how thick the ice layer would be, right? So by ascribing some absolute limit to the stability of the liquid, we can back out an absolute maximum depth of the ice 1H layer, okay? So we went ahead and did that for a few systems of interest. And it gives us some bounds, between like 150 and 180 kilometers for the ice 1H layer on several interesting icy bodies of pressing current interest. Now, I will note that you know, the cenotectics that we've explored so far are all in the context of binary systems, right? So we need to either validate the 22K 200 MPa rule of thumb for higher component systems, or figure out how the cenotectic evolves when there's 2, 3, 4, 5, 6 components instead of just 2 components, because of course it's very unlikely that one of these oceans is just water plus 1 salt, right? We also need to think about how organics contribute to the thermochemistry of these systems, how that would depress the cenotectic further, or could. And then we need to find an experimental way to deal with these high pressure hydrates, so we're not sort of limited by metastability issues there. But so that gives you a an overarching sense of our mission with this low temperature, high pressure thermo. We've sort of intellectualized this idea of the absolute limit, and now we've characterized it for a couple of systems, but we need to hunt it farther and farther until we know this limit, the cenotectic limit, for system chemistries that we think are truly representative of the complexity of one of these icy ocean worlds. Okay, so that's my 5-second overview of the understanding icy worlds portion. Now I want to talk a little bit about biopreservation, and of course this is a planetary science group, so I'm going to link it back to planetary science, but you'll forgive me the digression, and I promise it will all make sense at the end. Okay, so the other big thing that we work on using low temperature water thermo is biopreservation. So top level, for those of you unfamiliar, the problem that we're trying to solve in biopreservation is that biological matter has a shelf life, and this is frequently inconvenient to us, right? So our goal is to use low temperature aqueous thermodynamics to extend this shelf life. So there's really sort of a rich motivation space that we work within. I give you four examples that comprise most of the funding for my lab. So firstly, in medicine, there's a huge space race right now to figure out how to cryopreserve human organs for transplant. We actually have this really interesting situation where we have this huge number of people on the organ transplant waiting list in America, and yet simultaneously a majority of the transplantable thoracic organs that emerge from donors get thrown in the trash because we simply cannot get them into a recipient fast enough because we can't hold them outside the body. So if we could just manipulate the thermodynamics of water at low temperature in such a way as to stabilize them outside the body, we could transplant all of these organs and save thousands of lives next year, right? In agriculture, similarly, we have this ballooning global population and disproportionately ballooning global hunger driven largely by climate change. And we have simultaneously 30 to 40% post-harvest food loss across the planet, right? So we have this huge hunger problem, and yet we're throwing out so much food. Likewise, the food that we are able to store for prolonged periods consumes a huge amount of global electricity, further sort of cyclically enhancing the problem. And so there's also critical needs in biopreservation to find new ways to extend the shelf life of fresh foods while decreasing energy consumption instead of increasing it, right? In the conservation space, you know, we're grappling with global biodiversity that is vanishing at a truly alarming pace. One thing that I always point out that shocks people is that a third of the coral in the Northern Great Barrier Reef were lost in a single bleaching event in 2016, 2017. It's estimated by 2030 we'll have approximately 2% of the current genetic diversity left in the Great Barrier Reef. 100,000 plus species of flora under threat of extinction. One method that increasingly, you know, leading conservation entities like the Smithsonian National Zoo are pursuing and working with us on is trying to biobank this genetic diversity while it's still here on the planet. Use cryopreservation to sort of preserve what we have here on Earth before it's too late. And then finally, you know, related to the planetary science angle in some ways, you know, NASA increasingly is thinking very hard about whole astronaut biopreservation, looking at the sort of, you know, Planet of the Apes, trip to Mars cryochamber, right? So you think even 20 years ago, the idea of NASA funding whole astronaut cryopreservation was totally ludicrous, whereas, you know, last year, NASA Trish had a $20 million call looking for ways to cryopreserve entire astronauts, right? So the science of cryopreservation is leaping out of the pages of science fiction and becoming a fact and reality very quickly. A lot of different application spaces here, right? All dependent on good low temperature water thermo, fundable by a wide variety of federal government organizations. So do with that info what you will, if any of you are low temperature water thermo people. Okay, so why is low temperature biopreservation hard? Well, first of all, why does it work, right? It works because the sum total electrochemical reactions that we think of as life, these are all roughly Arrhenius temperature dependent, right? So as we decrease the temperature, the simple rate at which life and the expiration of life happens is slowed down. Now, the challenge here is that the temperatures where we get really, we get to the metabolic rate depressions where we can really preserve things for a long time, months or years, are much lower than the freezing point of water, or the melting point of water, I should say. And in most of the biological matter, complex biological matter that we're interested in, ice formation causes irreversible damage. So we have this really, really fundamental challenge where we need to find a way to keep things like us and our organs that are mostly water really cold, sub-zero, but not allowing them to freeze, right? So our sort of general solution here is to manipulate the thermodynamics and kinetics of these systems to stabilize water at low temperature. So you can see here this sort of obvious conversation that can happen between my community, the cryopreservation, cryobiology community, and you guys as sort of icy worlds, astrobiology, space community, right? Where in the context of icy worlds, we need to understand the thermodynamics of water at low temperature and the limits of stability. We need to understand the building blocks for life at low temperature, how life might thrive in extreme environments. And in biopreservation, we're trying to engineer those same thermodynamics to push the limits of stability. We're trying to manipulate those building blocks of life at low temperature to adapt for extreme environments, right? So the foundational knowledge that needs to be built for both of these fields is exactly the same. Just the motivation is a little different. But there's a huge area, where meaningful crosstalk can happen. And we're starting to do this at a systematic level. So I'm on the board of governors of the Society for Cryobiology. I'll shameless plug. We have a seminar coming out with some people you guys might recognize. But these are all planetary scientists. We're going to be talking about, the opposite of what I'm talking about right now, how planetary sciences can come aid the understanding of the state of cryopreservation. So if you're interested, send me an email. I'll send you the link to this. It's going to be great. Okay, so my original life plan today was to now go into talking about some work that we're doing on the modeling and synthesis of complex aqueous organic solutions. I think looking at how much time I have left, I don't want to do that, and I would rather just cut and take some questions. But let me just do this. I'll do a tiny plug in case there's anyone watching who's interested in organics. The TLDR here is that we've developed some new ultra high throughput analytical thermodynamics approaches for predicting based only on pure component data and using only classical thermo, the phase diagrams of aqueous organic systems, both in binary form and then also in, we're now predicting ternary phase diagrams where we can isolate the ternary eutectic and it'll agree within a few degrees with experiments. And it's a generalizable technique that can go to n components. So it's a really interesting new modeling approach. So we're using this to design arbitrarily stable, biocompatible low temperature fluids. But I think there's some really interesting intersections that I want to explore with the icy worlds community, trying to see how the presence of some of these token organics that have been found in various space environments, things like acetone, methanol, and then things that might be the result of prebiotic synthesis in some of these icy worlds, you know, like sugars, amino acids, start wrapping these into our understanding of the limits of temperature stability in liquids on these worlds right now, right? Because like a lot of the literature that I see out there on icy oceans is thinking about the salts, the inorganic components, right? Or it's a separate group thinking about methanol, right? But there isn't sufficient crosstalk at this point looking at 4 or 5 component chemistries where we take the salts and the organics and we see how, you know, the coupling of all of these different, you know, entropic and enthalpic effects might be driving the stability of the temperature of the liquid way lower than anyone thinks. So if anyone has any interest in organics, in icy world, space, whatever, please come talk to me. We're really excited about this modeling approach and want to find some interesting ways to use it. So with that said, yeah, I mean, we've made some independent, separate progress in the thermodynamics of high pressure, low temperature salt systems, and new progress in many component organic systems. We're starting to merge these things together with the goal of creating a more coherent thermodynamic description of the limits of liquid stability for mixed organic, inorganic aqueous systems of arbitrary chemical complexity at arbitrary pressures, right? So we're trying to be the stability guys, right? If any of you are interested in working on that with us, and or if any of this information can be of any use to anything that you do, please send me an email. Okay, thank you very much. Shout out to my Rockstar grad students and collaborators and NSF for giving me dollars.
All right, do we have questions for Matt? Maybe starting online, do we have any questions?
Do I need to have this computer's
No,
speakers?
come to this.
Oh, okay.
Go ahead, Chad.
Yeah, great talk, Matthew. So I have a maybe a very naive question. So in order to follow this isochoric methodology, do you have like in your experimental apparatus, can you directly see the 3 phases?
Yeah, so in the version for which I've shown data here, you cannot. There's no optical window. The newer ones we're building, there is also an optical window. Yeah, so maybe that answers your question. I think there's a lot of interesting promise for taking this isochoric technique and marrying it with things like Raman spectroscopy and other sort of optical phase evaluation stuff. Huge parameter space to be explored here experimentally, really exciting. If you're an optics guy, please let's do it ASAP. Yeah, does that answer your question?
Kind of. So I have actually a follow-up. This first part, this is the second part. So if you cannot see the 3 phases, how can you guarantee you're right at the eutectic?
Yeah, great question. So a lot of it is based on faith in classical thermodynamics, but I'll go back to this slide here. So, you know, this is sort of ultimately the best way to do your due diligence and verify that what you're seeing is the eutectic line, right? So we start from the eutectic composition. We hope that when it crystallizes, we're getting both the crystalline phases and we're getting the eutectic configuration. But you can always check by checking, running the same test with an off concentration, you know, like a couple % higher or lower than the eutectic. And if indeed you were measuring the 3-phase eutectic in the first place, those 2-phase lines must join the 3-phase line. They must all converge to the same line, right? And that line, if all the 2-phase lines converge to it, is definitionally the 3-phase eutectic line. Does that make sense?
Yes, but in the meanwhile, the eutectic will also shift to, like you said, the composition will also shift, right?
Yeah, so it's, you know, it's a totally closed system. So as we evolve in temperature and pressure, the concentration of the liquid phase is changing due to solute rejection, for sure, right? So right now we aren't, you know, we know the total composition in the system. We aren't measuring the composition separately, So this is why, you know, we have
I
temperature pressure lines, but not temperature pressure composition lines. So to get to temperature pressure composition, you have to go one more step and incorporate some knowledge of the solute phase, the solute bearing solid phase liquidus surface.
Sure. Yeah. I guess I would confuse because in previous slides, you have the pure water and I think 20 weight percent of sodium chloride. I saw these are the eutectic dissolved sodium chloride compositions or concentrations. I think that was
Oh, sorry, yes. So those are the starting liquid compositions, and thus also the total composition in the system. Yep.
Sure. Yeah. Thanks.
Yeah.
Cool. Any additional questions? In the meantime, I have a question. So, so I'm a geoscientist, right?
Yeah.
And so you take igneous petrology and you all talk about eutectic. Oh, well, you probably don't. You're not a geoscientist, but when we talk about melting rocks, we talk about eutectics and other such phase diagrams, right? But if you then take sort of an environmental aqueous geochemistry class, that's like seems a completely different world, right? And here those two worlds sort of come together.
Yeah.
Sort of, I guess the aqueous geochemists are much more concerned with describing complexes and the solute. They don't never talk about it, eutectic point.
Yeah.
Right. So you seem to be coming at it very much from a phase behavior type side, but there's the whole world of what actually happens in the liquid.
Mm-hmm.
Right, like how is the salt distributed and how does it interact? Does it soak to the surface? Is that at all something that you think is that relevant or?
Yeah, I think it becomes relevant after you've figured out
The phase
behavior. I mean, I think the most shocking thing to me when I first started reading this icy worlds literature was just like how little we know about the most basic thermodynamics of some of these systems, so just the phase behavior. And then from there, you can build up all of this beautiful sort of molecular level understanding. Once you've created the foundation of the bulk behavior classical thermodynamics. That's my attitude. Some people argue the exact opposite. You want to start with the molecular level and try and get to thermodynamics from there. But I think it, in terms of efficiency of getting to the information that will be most interesting to us from a planetary modeling or interpretation perspective, we want to get the thermo first and do the molecular level understanding next.
Yeah, I've got a question. So maybe I have two. One is you might be able to define, it looks like, the maximum thickness of the ice shell by defining that limit. I'm curious if you go the other way. What's the thinnest you can still maintain the ice shell? You go the other direction with those curves.
Yeah, I think you can. It's the same calculation, except for it's just now limited by the low temperature,
right,
or the low pressure behavior. Is that a more interesting question to ask?
So it is in some ways because of the observational constraints of some of the instruments going there.
Yeah.
For instance, in general, that radar doesn't. Well, most people will think the radar that's flowing here from UT is actually going to see through the whole thing. So most people think it's thicker than it will see. But how thin can it be? The number has been thrown out there, and maybe 10 kilometers. People argue it's possible.
Yeah.
Most people think it's more like 30 or 100, right? Something much more. But could you completely independently make an argument for how?
Yeah, I
it's
think
possible.
The tricky part on the warm side, right, is that the limit of stability for the liquid on the warm side is the transition to vapor, right? So you have a huge headroom here that's now dominated by what could plausibly be happening from a heat transfer perspective, and not from a thermodynamics perspective, right? So it's harder to do, but there are similar arguments I think you could apply.
Oh, are we done?
Yeah, it's class in here, yeah.
Yeah. Okay.
Sorry. Yeah.
Thank you, everyone online.